Hello?
Yonca.
Can you hear me? Hi.
Yes, I can hear you. Can you hear
Perfect.
me?
Yes.
Maybe we can try to share the screen just to be sure.
Okay.
Okay,
Can you see?
I can see, but it's not in presentation view.
Yes. Do- How's it now?
Yes. Okay, it's fine now. Perfect. Try to change the slide to see if it's fast
Yeah.
or not.
Let me pick the pointer.
Yeah,
Is it moving? Yeah.
it's fine. It's fine. Okay,
What?
perfect.
Okay.
So
What if I switch to
you
present? No. Ye- Is it still in the same?
in this case, no, it's not the same. I can see
Okay.
also your following
Mm,
slides. So this way is better.
okay. Yes. Okay.
Yeah. Okay, so see you in few minutes. I will open my camera and I will advise you when I'm starting the registration.
Okay.
And
Okay. Okay. Perfect.
okay, fine. See you in few minutes.
See you.
Are you there? Okay.
Yes.
In a few seconds, I'll start recording.
Okay.
Good afternoon to everybody. The seminar of today is a functional thin film by layer self-assembly and is presented by Yonca Belce from Institut de Recerca de Energía de Catalunya. Dr. Belce is a chemist who has obtained her PhD in material science and engineering from Sabanci University. Her PhD, entitled Functional Thin Film Coatings and Porphyrin and Phthalocyanine by layer assembly, was fully funded by TÜBİTAK, the Scientific and Technological Research Council of Turkey. In 2020, she joined the ChemInflow group at the University of Barcelona as a postdoctoral researcher. Her research was focused on synthesis and controlled growth of two-dimensional porous crystalline molecular frameworks via microfluidic technologies. Currently, she is working as a postdoctoral researcher in the Energy Storage, Harvesting and Catalysis group at the IREC, Institut de Recerca en la Energía de Catalunya, under the supervision of Prof. Morante. She's developing new electrolyte compositions for effective vanadium redox flow batteries. So, Yonca, thank you for accepting the invitation, and when you are ready, the floor is yours. You can share the screen and start.
Hi, everyone, and thank you, Sarah, for your kind invitation and introduction. So let me share my screen first. Okay, can you all see?
Yes.
Perfect. So as Sarah already introduced, today I'm going to talk about functional thin films by layer self-assembly, which was part of my PhD thesis in Sabancı University. So I know that the audience is pretty multidisciplinary, so I would like to give a brief introduction on certain topics like macrocyclic compounds, mainly on layer self-assembly, which is the experimental technique here, and a brief review for the corrosion kinetics for the second part of the talk. And then I will focus on the influence of pH and concentration on layer self-assembly for the nickel phthalocyanine coatings. And then I will give you an example in terms of application. So where can we use these studies? And one of them would be the corrosion. And then I will conclude and give you some outlook. Okay, so to start with porphyrins and phthalocyanines. They are known as macrocyclic compounds. So due to their ring structure, they have at least, they should contain at least 12 atoms. And they are known as cyclic tetrapyrals, phthalocyanine and porphyrin. So they are unique due to their 2D π-conjugated structure, which means they have delocalized electrons due to this pi structure. The phthalocyanines are usually known as and they usually known as synthetic group of hydrophobic microcycle system, while the porphyrins appear, sorry, let me put the pointer. Porphyrins has more, oops, they are known as natural dyes. What I mean is actually you can find these porphyrins naturally in your environment. So chlorophyll or vitamin B12 or even hemoglobin are some of the examples that we can find in nature for porphyrin. So you can either have metalated or unmetalated porphyrins or phthalocyanines, depending on the applications you need. So as I said before, they have unique properties, and these properties give them high electrical heating and conductive properties. So here you can see some examples. So mainly in the visible range, the phthalocyanines exhibit the Q band, we say, between 480 to 750 nanometers. And that's where they have the most intense peak due to the pi-pi interaction. And the porphyrins usually have in the over frequency 380 to 500 nanometers. So just to give you an idea, so we can have cationic or anionic microcyclic compounds, either porphyrin or phthalocyanin, and mainly they are known as to be hydrophobic compounds actually. But in order to have them highly water soluble, you can add hydrophilic functional groups like hydroxyl groups, carboxyl groups, or amine groups so that you can dissolve them in water and apply on whatever you need. So mainly these phthalocyanins are applicable in many different areas in the literature, like photodynamic therapy, which is widely used nowadays in cancer treatment, in solar cell applications, or as electronic sensors. So phthalocyanins are pretty common, and we'll see in the upcoming slides an example how to embed them in structures. So let me move to the layer by layer self-assembly, which is the main deposition technique that I was using to obtain these thin films. So to start with, if a material, well, diversity of materials have multiple functions, and this gives a property of functionality to a material. So in order to have, let's say, functional properties, in the literature, three thin film deposition techniques have been reported. So first of them is the self-assembled monolayers. It is first discovered in 1980s. And here the main idea is actually you have a monolayer on top of a substrate, and in order to form organic thin films, you need surface active groups. So you can see here the surface active head of your chain. You have an alkyl group, and then you may have a mono or a hydrogen bonded group on top. In addition to that, in 1900s, there is another technique, thin film deposition technique, that is named after two researchers, Irving Langmuir and Catherine Blodgett. Actually, this technique requires a specific condition. You need to have an amphiphilic molecule, which means that you should have an hydrophobic tail, which is usually a hydrocarbon chain, or you should have a hydrophilic head, which is a polar functional group with a hydrogen bond. And in order to form a monolayer, you need an air-water interface. So what they do is actually they dissolve the amphiphilic molecule first in the organic volatile solvent, and then they gently put it on the aqueous subphase. And then by the help of a Langmuir through, it's possible to transfer the monolayer to a solid substrate. Once you have this layer transferred to the solid substrate, you can have a Langmuir-Blodgett film. But here the crucial thing is you need to have hydrophobic and hydrophilic interactions. So this is the most important part. either with the substrate surface, with the molecule, or vice versa. So that's why actually layer by layer technique opens a wider and more options to the literature. So here, actually, you can form multi-layers, not only monolayers, and you can pick any kind of substrate. So let me explain it more deeply. So layer by layer, deposition is known as an environmental friendly technique because we actually only need water. You don't need any volatile or organic solvents. So that's why it's simple and low cost. So as I said, it's water-based. So mainly the interactions are electrostatic, but you can have molecular interactions like hydrogen bonding, covalent bonding, so it's not only limited to that. In order to have a control over thin film morphology and thickness, you need to check certain parameters. The material concentration, pH, ionic strength, in some cases temperature, and the molecular weight. So these are the parameters that highly influence the overall thin film properties. So let me give you 3 examples of layer by layer preparation methods. So one of them is the dip LBL. So what I mean is you have a substrate, you dip into your coating solution, dip it there, let's say 10 minutes, and take it out, put it into the second solution, which is mainly a rinsing water bath to get rid of the excess material on the surface. And then you dip the substrate into the second coating solution, and you wait there again 10 more minutes, and then you rinse it again in the fourth bath. And you can continue to do that as long as you need, 100 times, 10 times, depends on your needs. And spray LBL, so the idea is the same. Instead of dipping, you just spray out the material on your substrate in a sequential order. And again, you can repeat it as much as you want. And finally, the spin LBL. So you put the substrate on top of a rotating disc, and then you drop cast your deposition material. You spin it at a certain rate. Then you repeat the same process as much as you need material 1, material 2, material 1, material 2, and so on. So layer by layer applications are pretty common in literature. So I'll try to just give some of the examples, but there are really many, and it's increasing day by day. So one of them is imagine that you have a metal and you want to protect the metal. So that's from corrosion or anti-gravity. So you put layer by layer polyelectrolyte multilayers on top of each other, and in this case, so that you can protect underneath metal. Or you can use in bio applications, or you can use it for membranes. So imagine you have a membrane, but you want to diffuse certain materials, not all of them. So you have a controlled diffusion by applying the necessary coatings. This example is one of the most interesting ones. Sorry, because it's pretty hot topic. So you imagine you have a microneedle, and they coat the surface of the microneedle, and they actually use these injectable microneedles in different treatments. So you can put it on a patient's arm or wherever needed, and you can just transfer the coating, not the needle, and it's painless and easy. Also, you can use antibacterial surface coatings on implants, or you can use biomolecular immobilization for sensing on biofuel cells. So there are many different applications in layer by layer study. So here I will give a brief information about the corrosion kinetics. So this will be for the second part of the talk, just to give you an idea for the application part. So there are many ways to measure the corrosion of a material. So there is not only TOEFL. but this is one of the methods that I was focused on. That's why I will now explain you a bit the technique. So you need the anodic and the cathodic reaction. So once you have an anodic cathodic reaction, you can plot it in a current versus potential graph. So at the corrosion potential, the anodic and the cathodic reaction tends to have at the same rate. So what means is actually at the corrosion current, at corrosion potential, the anodic and the cathodic currents are equal to each other, which is giving the corrosion potential. Let's say you have an iron, it's going to oxidize in the anodic reaction, and in the cathodic part you will have the oxygen, and it will be reduced to the OH. So it's quite impossible to have a direct measurement of potential and current relationship of these half cells individually, but we can measure the net current by using a 3-electrode setup, and this is what I did in the study. So at corrosion potential, the anodic cathodic current cancel each out, but let's plot this in a logarithmic x-axis. So be careful, here you have the logarithmic current in absolute values, and you have the potential, and you have the cathodic and anodic parts. At the point where they intersect, you have the corrosion current. And actually, this is what we need. So by extrapolating these lines linearly, you can calculate the anodic and cathodic TOEFL, which will give you the beta A and beta C slopes. And while putting into the necessary equations, you can calculate the net current and therefore the corrosion rates. Okay, let's go into detail about the results. So first, I want to show you how actually pH and concentration influence the thin films. So first of all, the films. In order to prepare the films, I was using a customized layer by layer device, and this is dipping and spinning simultaneously. So I have my substrate, I have the solution I need to deposit. I'm dipping and spinning at 100 RPM my substrate for 10 minutes. And then I'm taking out the substrate and putting into 3 different water baths so that I can rinse the surface, get rid of the excess material. And then I'm dipping and spinning my substrate again to deposit the oppositely charged material on surface. And I do it for 10 more minutes and then rinse it again. So here mainly I'll check the pH and concentration of nickel phthalocyanine, not the supporting layers. So what I mean by supporting layers is, so this is the general scheme of film. So the bottom is the substrate. You can have anything you want, glass, quartz, silicon, metal, whatever you need. The red and the blue ones are actually adhesion layers. They are really, really thin layers. They are just needed to enhance the interaction between the upcoming layers and the substrate, but they don't play a role in the overall film properties. And then I introduced the positively charged polyelectrolyte, which was branched polyethylenamine in this case. And then I was introducing negatively charged phthalocyanine, which is the nickel phthalocyanine. So, as I said, I was changing the pH of the phthalocyanine only. And these are the chemical structures of the branched polyethylenamine. So you can see the polymer chain here and the amine groups attached to the branched polyethylenamine. And the phthalocyanine has the sulfonated groups, and that's why they have electrostatic interactions, and they are both water soluble. And actually, these are the conditions that I've studied. So I've checked 2 different concentrations and 4 different pH values. So to start with, do we have any film? Yes. So by checking the photophysical properties by UV visible spectroscopy, we can confirm that the Q band of the water-soluble nickel phthalocyanine is visible in the solid form as well. And it's, as I said, it's around 600 nanometers in this case. Due to the advantage of the colored structure of phthalocyanine, we can actually do such a nice measurement. Thus, once you increase the number of layers, we are expecting to see an increase in the intensity, and this is what the case. So as the number of layers increases from 2 to 10 bilayers, so the black one represents the 2 bilayers of film, 4, 6, 8, and 10 bilayers. So at the maximum, you can see they are all growing linearly. Okay, growing linearly. Let's stop here because I need to show you how they grow actually. So, do they grow linearly? So in the influence of concentration, let's double or increase the concentration by 2.5 times. And what I was expecting to have a 2.5 increase in the thickness, but this is not the case. As you can see here, the initial thickness, overall film thickness was 80 nanometers, and in the increased concentration, you have it's around 100 nanometers. So why is it not really 2.5 folds? So we have an exponential growth. This might be due to a couple of things. First, it can be that maybe the phthalocyanine is interpenetrating into the underneath layer, or vice versa, the branch polyethylene, so that they are not providing distinct layers on top of each other. So that either one of them is swelling and diffusing. Or in addition to electrostatic interactions, they may have other kind of molecular interactions as well, like hydrogen bonding and so on. So it is not the only way. So let's see the influence of pH then. So here you can see how beautiful it is when the pH is in the acidic medium. But as you move to the basic side, you see almost a transparent film. So and I also checked the thickness and the absorbance of these thin films. And similar to the previous case, it's growing exponentially again. So here actually the reason behind could be that once you move to the basic side, to the basic medium, you may actually have your polyelectrolytes collapsing on the surface. So instead of having a standing structure, you may have a planar orientation, and that's why maybe they are involving less in the thin film structure. So actually, in order to monitor in real time the molecular deposition, there is a pretty good technique, the quartz crystal microbalance. And by using this technique, you can actually deposit your film and monitor the deposition in real time. So here you have a quartz piece sensor, which is coated with a gold. And on top of it, you introduce your materials one by one in a sequential order, as we did in the standard layer by layer study. And then you can monitor the change in frequency. So pH and SPS, they represent the adhesion layers. The BPI is our very first positively charged layer. And then once I start to introduce the nickel phthalocyanine, you see a sharp decrease in frequency. Here again, once you introduce the branch polyethylamine, there is, yes, a decrease, but it's not so intense. But as soon as you introduce the phthalocyanine, there is a sharp decrease. So actually, this is why we have deposition in a sequential manner due to the addition of nickel phthalocyanine, and it's really nice to see in real time. So in the first part, I can say that the concentration dependency is not linear, but it's exponential, but it doesn't have to be always the case, because I will show you in the upcoming slides that it's possible to have linear growth as well. Also, once you have an acidic medium, you have thicker films. And it's possible to control the thickness of the material by changing the acidic medium of the deposition solution. And you can monitor in real time the molecular buildup by quartz crystal microbalance. Okay, so we have seen how these parameters can influence the thin film, but can we use these multi-layers to apply for a certain purpose? Actually, yes. This is what I studied in my PhD. I want to just give you a short example of it. I will not go into too much detail. But what about corrosion? Because we know that these phthalocyanines has a metallic core, and they tend to sacrifice themselves once they are exposed to highly reactive singlet oxygen environments. So that's why the study is only aimed for aerospace vehicles. And what if we have these multi-layer coatings on metallic surfaces? And will these phthalocyanines sacrifice themselves and protect underneath metal? So to do that, I've studied two different architectures, a bilayer structure and a tetralayer structure. So what I mean is bilayer structure is exactly the same what you have seen in the before slides, in the previous slides. And the tetralayer structures, actually, I have more polyelectrolyte layers and phthalocyanin layers. So more phthalocyanins and then a single layer of phthalocyanins. So actually in the tetralayer structures, we have less contribution of the phthalocyanin. So in terms of numbers, I can say that the A structures, A, B, A1 and A2 represents different metalated phthalocyanins. So A1 stands for nickel phthalocyanin, A2 stands for the copper phthalocyanin, and they have 30 layers of phthalocyanin. S1 is just blank polyelectrolyte without any phthalocyanin content. And on the tetralayer side, as I said, there is less phthalocyanin, so 15 to 6 layers. And all of the electrochemical measurements are done in this unit cell. So what we have is a reference electrode, silver chloride, and a counter electrode, it's a graphite rod. And in terms of a working electrolyte, it's the sample that is coated. In order to simulate the atmospheric conditions for aerospace applications, dilute Harrison solution is used. This is one of the suggested electrolyte composition in the literature. So first, I need to check the thin film growth in both cases. I mean, both bilayer structure, tetralayer structure in the presence of nickel, in the presence of copper. And as you can see here, in the presence of tetralayer structures, we have an exponential growth, but in the presence of bilayer structures, we have a linear growth. This might be due to the higher concentration of polyelectrolytes in the overall thin film system. So they might be swelling, diffusing into each other, but we have here only single layers of polyelectrolytes after each other. And also I checked also the photophysical properties, and they totally match with the aqueous forms, and they preserve the Q band in the 600 nanometer for all structures. And in terms of thickness, what's interesting is actually also the bilayer structures with no matter with which metal you have the highest thickness overall. So you can get 200 nanometer thickness with bilayer structures. But once you switch to tetralayers, then you'll have a decrease in thickness up to 40 nanometers or so. Just to make a note, overall thin films have all same number of layers. Overall, they have 60 number of layers at the end. So what about the corrosion then? Do they really help? So to do that, I've checked the Tafel measurements, and here you can see the current density versus the potential for nickel and the copper case. So let me explain you what it means. So first of all, this is how it looks for the copper metalated film on a stainless steel surface, and this is how it looks on the nickel metalated film on the same metal surface. As the phthalocyanines are introduced to the thin film structure, we have actually almost tenfold decrease in the corrosion rate compared to the blank case. S1 again represents only the polyelectrolyte film. That it doesn't have any phthalocyanine content. So, and also once the nickel phthalocyanine is introduced to the system, there is almost tenfold decrease in the corrosion current density. Although the tetralayer structures also shift to more noble regions and in the presence of phthalocyanine, they don't show any significant change in corrosion rates. So actually, what we can say is actually, yes, they help to protect the underneath surface, but not always. The studied architecture also plays a role. So you have to make sure that you have desired concentration of phthalocyanine, pH, and also the architecture is highly significant to have a proper protection. So to sum up, so bilayer and tetralayer multilayer thin film structure architectures with both metalated phthalocyanines are homogeneously prepared, and you can check them with different methodologies. Especially QCM is a great tool to monitor in real time, and you can actually control the thin film growth in nanometer scale, which is highly significant. And also, it's important to note that introduction of the phthalocyanines via bilayer architecture can enhance the protection. But again, you have to make sure that you have the appropriate one. And these studies are already published. And thank you for your attention. I'll be happy to answer your questions.
Well, Yonca, thank you for your very, very nice presentation. So as you told, this is the time for questions. Don't be shy. You can ask, or you can write the questions in the chat and I can read them for you. So, well, in the meantime, I want to ask you just a few curiosities. I know that these thin films are very useful for a lot of application. For example, optical ones. Can you tell us something more about the potential of the system?
Well, I haven't studied any optical application in terms of phthalocyanines, but it's true that they are pretty colorful and nice. That's why actually it's possible to measure their spectroscopy.
I mean, in general.
Yes, in general. But I mean, it highly depends on the pH, whether you have appropriate color or so. So if you increase it, decrease it, you can play with the optical properties of the material.
Okay. And do you know some systems based on this kind of thin film that are already commercialized, or some industry that are producing something with other molecules in general? I am thinking about.
In terms of conductivity or electrical ones, well, I don't really know, but the interesting thing is, in terms of photodynamic therapy, now it's getting started to be tested in patients. So actually, they are using phthalocyanines without any functional groups, hydrophobic ones, and they are embedding them into polymeric structures so that they can transfer them to human body, and they irradiate the phthalocyanin and activate it to use for photodynamic therapy applications.
No, it's very interesting.
Mm-hmm.
And in a specific way about the last example that you show us, if you want to apply that system to cover some surface and protect the metal, is expensive or it's viable?
Yeah, it's not so cheap, yeah, to be honest. Well, it's water-based, that makes it pretty cheap. But if you use a maybe synthesized phthalocyanin, you can reduce the cost. But compared to other systems with more volatile conditions, it's pretty straightforward and we can say cheap, yes.
Okay, well, are very versatile systems, I think. Well, so are there more questions or just curiosities?
This is Anna.
Yes,
Hi.
Professor Teti.
No, a curiosity is if these films can be applied, for instance, to medical devices, for instance, when you have the hip replacement. So is there any biocompatibility with tissues?
Actually, yes. I mean, in terms of layer by layer, I mean, without phthalocyanin, I should say. Here I had some of the examples. For instance, this one, they were using
Okay, I
as
understand.
for implants. Yes, so it should be biocompatible, so antibacterial and so on. So yes.
Okay, so the advantage, it's not in saying the resistance of the device, but on the say the defense against pathogens and these type of things.
Mm-hmm.
Is that the advantage?
Well, or selective diffusion, because I'm not really involved in the bio part, but could be interesting to study, yes.
Yeah, and another issue is always in the same field. Sometimes that instead of metal, that use ceramics.
Mm-hmm.
Does it work also on that, or is something has nothing to do?
Anything that water can stay on it is possible to coat for layer by layer. So this is general.
Okay, thank you.
Thank you.
Any more curiosities? Well, seems not. So, if there are any more questions, thank you again, Yonca, for accepting my invitation. And I think this is the last meeting of the year. So we will see again in January with new seminars. So
Yes,
have a
Sarah, for this, we are having a Christmas party. We called it Porta Party. Everybody brings something, but I know that you are not here, and also the speakers are not here, but maybe you can join us virtually, just to have a toast together. This will be on next Thursday, I think. Instead of the TMS webinar, we will have this toast.